Prime resonance, a spectral reading of the Riemann hypothesis. For over a century, one question has sat at the center of mathematics. Why do the prime numbers fall where they do? This presentation offers one way of looking at that question. The prime numbers treated as the fundamental vibrations of a system, and the Riemann zeros as the places where those vibrations cancel. Each scene comes in two passes. First, the picture in plain language. Then the formal statement for those who want the mathematics. Think of a guitar. It sounds like a guitar because its physical shape constrains the energy inside it. A container acts as a strict boundary, dictating exactly which fundamental vibrations, or primal modes, can exist within it and which cannot. The prime numbers are exactly this, the primal, indivisible modes of the number line. Formally, we treat the prime numbers directly as the fundamental eigenstates of a physical system. We construct a prime-based Hilbert space where primes dictate the irreducible resonant frequencies, and a logarithmic weight function ensures square summability. These primal modes then assemble. When prime frequencies synchronize, they form composites. A composite presents a singular external interface, but internally it is a complex product structure of primal modes. Thus, primal modes create composites, and these composites become new containers themselves, forming an infinite recursive loop. Formally, the Euler product formula establishes the physical equivalence between the macroscopic field and its constituent prime harmonics. The sum over all integers represents the total partition function of the interference field, while the product isolates the prime standing waves. This recursive loop is true whether the modes are physical waves or conceptual numbers. This is why the distribution of prime numbers looks exactly like quantum chaos. They are governed by the exact same spectral principles. The space of numbers acts as a massive spectral system, and the Riemann zeta function is the ultimate container for that system. Formally, every term splits cleanly into two independent physical quantities. The real part of the exponent governs the amplitude envelope, how strongly each mode contributes. The imaginary part governs pure phase, the oscillation that carries the interference. Numbers, the very perception of difference, act as the closure that enables anything to exist at all. In this infinite spectral field, there are specific frequencies where the crest of one primal mode perfectly cancels another. These points of absolute silence or total destructive interference are the Riemann zeros. Formally, evaluating this superposition across the complex plane reveals chaotic fluctuations in amplitude. At specific frequencies, the geometric arrangement of all prime harmonics balances entirely. These topological null states, points of absolute destructive interference, correspond directly to the non-trivial zeros of the zeta function. If we map every point of silence onto a plane, a startling pattern emerges. The zeros never scatter. They fall into a narrow band, and inside that band they stack up along one perfectly straight line, as if something is holding them there. Formally, plotting these null states in the complex plane, every known non-trivial zero falls inside the critical strip, between real part 0 and 1, and every one of them, without exception, has been found on the single vertical line at real part 1/2. For infinite primal modes to cancel each other out perfectly, the container's energy must be perfectly balanced. If one frequency decays too quickly, the silence is broken. Perfect cancellation requires a highly specific balance of amplitude and frequency across the entire internal product structure. Formally, to formalize this resonance via the Hilbert-Pólya strategy, we construct a self-adjoint block chiral operator, H. Its kernel mathematically enforces the phase coupling between prime states using an oscillatory localization term, modulated by bounded coefficients to satisfy Hilbert-Schmidt constraints. We can prove this by defining a strict mathematical rulebook, an operator, that governs how these modes share energy. It enforces a fundamental law. To achieve zero energy, the primal waves must align with perfect, unbroken symmetry. Formally, this operator possesses an anti-commuting chiral symmetry, ensuring a strictly real and symmetric spectrum. By calculating the wave trace, we find the spectral determinant of H exactly matches the completed Riemann C function. Because H is self-adjoint, its eigenvalues lambda n are strictly real. Consequently, the variable t is strictly real, physically binding the zeros to the critical line. Watch what happens when that law is applied. The chaos organizes itself. Every wave turns to face the same direction, and the points of silence line up like beads on a thread. Formally, under the operator's constraint, the prime modes can no longer be arbitrarily oriented. Their phases lock. The chaotic field collapses into an ordered standing wave, and the nodes of that standing wave arrange themselves along a single axis of symmetry. The Riemann hypothesis asks where these points of perfect silence exist. By viewing numbers as a system of nested containers and primal modes, the answer becomes pure geometry. Absolute silence can only exist at the exact midpoint of the system's energy. The critical line is that exact geometric center. Formally, the prime resonance framework formally unites spectral geometry with number theory. By constructing a self-adjoint Hamiltonian whose spectral determinant equals the completed Riemann C function, the Hilbert-Pólya conjecture is satisfied. The geometry of the prime field dictates that perfect destructive interference can occur only where the amplitude envelope achieves absolute phase symmetry. The critical line is this exact geometric boundary. So the picture closes on a single idea. Primes are the irreducible modes of number. Their interference builds the zeta field. Silence in that field happens only where amplitude and phase are in perfect balance, and that balance lives on one line. The formal resolution of that idea remains one of mathematics' open questions, but it turns an abstract conjecture into something you can hear, a system that can only fall silent at its own center. Thank you for listening.